So, we were looking at various steps which are involved in analysis of discrete time response of systems. In the previous lecture, we looked how we can sample a continuous system to obtain a discrete time system, and how we can convert a discrete time output from the controller back to a continuous signal. The only step which is left is the conversion of a continuous time model to a discrete time model. So, let us look into this particular aspect. Now, we will study the conversion of continuous models to discrete time models, and let us also understand that we are doing this with specific relevance to the response or the dynamic response of the system. So, we have already looked into conversion of models from continuous time to discrete time. This particular effort would be dedicated to have a system such that we can analyze the response, the dynamical response of the system. Okay. So, let us first look into a very general first order system. So, the system is given by, let us say, A 1 dy by dt plus A 0 y is equal to b times u. The equation is in deviation variable form. So, we know that everything is normalized. So, at time t is equal to 0, you introduce the disturbance. So, y starts from 0. Okay. So, to convert it to discrete time form, let us make small changes. Let us write it as A 1 by A 0 dy by dt plus y is equal to b by A 0 u. We are doing it for convenience to club the quantities to physically important variables. Mathematically, this same procedure can be done without this division as well. So, when the equation is cast in this particular form, we know that we can write this as tau dy by dt plus y is equal to capital K times u, where tau is A 1 upon A 0, the time constant associated with the system, and b k is equal to b by A 0, the static gain of the system. So, now let us convert the equation tau dy by dt plus y is equal to k u to a discrete time equation, and we will use the definition of the derivative as follows. I will write dy by dt is equal to y n plus 1 minus y n upon capital T. Okay. So, why is this the definition? We are converting time in discrete domain. So, I say that my sampling of the signal takes place in this manner, that I have 0 and this is my time. So, the next sampling would be done at capital T. So, delta t of time is capital T here. Further, I will have 2 t and so on. So, therefore, division is by capital T. Capital T is the interval in which the sampling is done, and y n plus 1 is the intensity of the signal at the next instant, given then get the intensity of the signal is y n at the current instant. Okay. So, if this is the case, then I can write my dynamical equation as tau upon capital T y n plus 1 minus tau upon capital T y n plus y n is equal to b upon capital K, rather capital K u n. Now, u is your forcing function that may also be a function of time. So, therefore, the intensity of your forcing function at given instant of time. So, that is u n. So, this will be tau by capital T y n plus 1 is equal to tau by capital T minus 1 y n plus k u n or y n plus 1 is equal to capital T upon tau T tau minus capital T y n plus T capital K upon tau u n, which finally gives me the model equation as y n plus 1 is equal to tau minus T upon tau y n plus T capital K upon tau u n. This is my discrete time model for a first order dynamical continuous equation. Let me repeat, y n plus 1 is equal to tau minus T upon capital tau times the value or intensity of the function at the current instant of time plus T k upon tau times the forcing function, the intensity of the forcing function at that instant of time. Now, if I compare equation 1 with its dynamical analog, discrete time analog equation 2, what I can see here is that I already have the dynamical discrete system in such a form that I get already an idea of the evolution of the system. See, the whole point of doing this analysis right from the day 1 is to determine the evolution, the time evolution of the system, and when you have the dynamical equation, you do have an idea about the time evolution, but in an indirect manner, that you first need to explicitly solve the dynamical equation for the dynamical variable, and then you can have an idea about the dynamics. But the dynamical equation in the discrete form itself has y of n plus 1, that means the intensity of the signal at next instant of time as a function of its intensity at right in the beginning, right. So, therefore, the form of equation which is there in the discrete time is quite convenient to get the evolution. Let us see if we can have an idea about the evolution of the system with the help of this particular equation. So, we said that if I have a first order equation and u of t, the continuous time forcing function, as a step function of magnitude a step input of magnitude a, then I know that y of t is equal to a times k 1 minus e to the power minus t upon tau, right. This was the solution which I obtained in one of the previous lectures. So, now what I can do is I can plot y of t versus t. So, I have this equation y of t as a function of t, and what I am going to do is I know that if this is a, then for k is equal to 1, unity gain, my response is going to look something like this. Asymptotically, the response curve will reach a. This is what we solved, and this is for continuous domain. Can we look into this equation, equation number 2, and see if we get a similar solution? So, let us try to do this. My equation here is, so the parameters associated with my system are tau tau, then capital T, capital K the gain, and u. Okay. And for a step input, u would be simply a constant. So, u of 0 is equal to u of 1 is equal to u of 2 is equal to u of n is equal to u of n plus 1, that is everything equal to a, right. So, let me assign some values. Let me say that my time constant is 0.1, time constant is 1. The sampling time, we said that in the previous lecture that the sampling time must be smaller compared to the time constant, so that you get the correct dynamical characteristics. So, let me make the sampling time as 0.1. Let us consider a unity gain and unit step input, okay. Everything is 1. So, now my what I have here is y n and y n plus 1. I will get rid of the text so that you can see it clearly. Let me just punch in the formula. So, this is equal to tau minus t. So, tau minus t divided by tau, the whole quantity multiplied by y n. Okay, so, this has to be y n plus 1, sorry. Let me give some. So, initial value of y n will be 0. So, this is equal to this, and let me complete the formula. This plus t k u n t into k into u n divided by tau. Okay. So, this is my whole formula. Let me now get rid of the text and let us see if this is the formula which I get, if I have used correct formula. Okay. So, tau tau minus t divided by tau multiplied by this has to be times y 1, okay, plus t into b 2 is so tau into k into u divided by tau. Okay. This is the formula, and what I need to do is I need to make all of these quantities constant. So, everything with b would be a constant. Okay. And then what was our recipe to propagate the system? We used to make y 1 as y n plus 1. So, let me see if I can propagate the system like this. Yeah. Then let me simply plot this. I will insert a plot, and let me insert a scatter plot. Okay. And what do you see here? Well, you do see that. So, let me make one more change. What you see here is that you start with 0 0 and you move here. Well, I can as well do one thing. I can make one more change. I can propagate the system further. Okay. And then what I can do is I can plot, I can make this plot further. So, let me draw this entire plot, and what I see here is this, that I start with 0 0 and I get a trend which looks like this, right. And what is on the y axis? This is y. What is on the x axis? This is t, t n y n. Is this what we also got in the continuous domain? Yes, in fact we did, right. The plot looked like this, except that it used to come asymptotically to 1. Now, it also is reaching towards 1. Now, we can do one thing, we can change the parameters of the system, and let me make the time constant here little smaller, so that the dynamics becomes faster. And if I do that, you see that the response has shifted up. I can make it even smaller, 0.04. The sorry, I need to change the time constant. So, I will keep this same, I will reduce the time constant to 0.8. The responses become closer. I will make it a very small time constant like 0.5, and then you see you are actually reaching very close to 1. So, asymptotically you will reach 1 and you can play around. Now, instead of unit input, step input, if I put 2, what is going to happen? Now, instead of 1, it is asymptotically reaching 2. So, all the features remain exactly the same, right. So, in fact, we have one way to convert our continuous time model to discrete time model, and the qualitative features actually are captured correctly. Now, in this particular case, we took the example of a step function. Now, let us see what if we have a function which is a ramp function. Okay. So, I have a ramp input. So, I have u of t is equal to 80. U of t now is equal to 80. What would be the discrete time analog of this? How would you do that? Well, let us see if we can get it from here. I can write this as d u by dt is equal to a, from where I can write u of n plus 1 minus u n divided by t is equal to a. In other words, u of n plus 1 is equal to u n plus a t. This is the ramp input. What was the step input? The step input was u n is equal to a and so on. It was just a constant value for every n, right. Now, for ramp input, u n plus 1 is equal to u n plus a times t, where a is the gradient. So, now what we can do is we can plug in this formula in the previous analysis. Before we do that, let us see what was our input, what was our response to this kind of input. So, in continuous domain it was y of t and this here is t. So, our input looked like this. This is the ramp input, and our output, let us refer to one of our previous lectures, you will see that the output looked like this. Okay. So, input and the output. So, let us plug in this formula in the previous analysis. So, what we will do is this, let us get rid of this plot, and then instead of u is equal to 2, what you have to do is you have to specify a, okay, and let me specify a as say 0.5, the gradient which I have. So, now what will happen to the formula? I need to input the value of u n. So, this is u n, and what will be u n? U n is equal to, at initially u n is simply 0, okay, and what will happen to u n plus 1? Okay. So, u n plus 1 is equal to u n plus a into t. You see here u n has changed, right, u n plus 1 has changed, right. So, what we will do is this, let me make B 4 and B 2 constants. So, B 4 and B 2 would be constants, and how would u n evolve with time? I can simply do this. See, so if you want to see, if you want to ensure whether u n is really a straight line ramp function, just draw this function. You see, it is a straight line function, the straight line function. Okay. Fine. So, now what I need to do is I need to change my formula to where I need to change u n. So, let me get rid of everything here, and now what I will do is, in this formula y n plus 1, what I will do is I will not use this B 4. Instead of B 4, what I will use is F 2, okay, into F 2. Okay. And let me do this. Let us see what happens. Now, I have a function which looks like this, and let me plot the function. And see what you get. Okay. There is one small change which we would like to do. See, the reason why you got 2 zeros here is because this is u n, it has to be u n plus 1. So, everything has to be shifted by 1. Okay. Otherwise, you can see this as the time evolution of the system. This is a better way to see. So, I see the time evolution of the system like this. So, let me plot it like this to make it look very clear. What was our continuous time domain response? We drew the continuous time domain response as this, that y of t versus t, there would be an initial curve and then there would be a straight line which would be parallel to your ramp input. You get the same analysis here. Here is an initial curve and then you go and make a perfect straight line. Okay. So, therefore, you can say that the discrete time model which you developed here actually captures the correct characteristics, and we have verified it not only using step input, but we have also verified it using a ramp input. In both the cases you get the same response as what you got previously. Okay. So, now if we are sure that we have some kind of a recipe to determine the discrete time analog of a continuous input, can we look into the input output model and develop a single input single output model. So, our system in that case would be dx by dt is equal to ax plus bu, our dynamical equation, and y is equal to cx plus du. This is our first order input output model, input being u, output being y. I would like to develop a corresponding discrete time model. So, from equation 1 I can write x n plus 1 minus x n upon capital T is equal to C A x n plus b u n, from where I can write x n plus 1 is equal to 1 plus a t x n plus b t u n. So, let me refer this to as equation 3. In this particular case, I have not done the initial rearrangements. Mathematically, it is all correct. There is not an issue as far as the steps are concerned. Similarly, for equation number 2, I can write this straight away as y n is equal to c x n plus d u n. Now, this should suffice, except that in equation number 4, I have x n, which has unnecessarily come up here as the dynamical variable. I may want to get rid of it. So, let us see if I can do something. So, from equation number 2, I can write d y by dt is equal to c dx by dt plus d times du by dt, right, and therefore, this can be written as y n plus 1 minus y n upon capital T is equal to c upon capital T x n plus 1 minus x n plus d upon capital T u n plus 1 minus u n. Okay. Now, I have x n plus 1 minus x n upon T simply as a x n plus b u n, right. So, I can write this as y n plus 1 minus y n upon capital T is equal to c times x n plus 1 minus x n upon T is equal to a x n plus b u n, okay, and this is equal to what? Plus d by T u n plus 1 minus u n. Fine. Now, let us see, can I make some rearrangements? What I can do is this, I can write this as y n plus 1 minus y n upon capital T is equal to a c times x n plus b c times u n minus d upon T u n plus d upon T u n plus 1, right. I still have x n with me, but I can use equation number 4. From equation number 4, I have x n is equal to what? Y n minus d times u n upon c. Now, I have y n and I have u n. So, from here I can write y of n plus 1 minus y n upon capital T is equal to a y n minus d u n, c c get cancelled out, plus b c minus d upon T u n plus d upon T u n plus 1. Okay. D upon T u n plus 1 plus d upon T u n plus 1. Now, see what we have here. I have y n plus 1, the value of the output function at next instant of time, and let me refer this to as equation number 5. The value of the output function at next instant of time minus y n, the value of the output function at right this moment, is equal to a y n minus d u n, the value of the input function at this instant of time, plus b c minus dt u n, again the value of input function at this instant of time, plus dt d upon t u n plus 1, the value of the input function at next instant of time, right. So, as we did this analysis previously, you can have u n plus 1 for a ramp function is equal to u n plus a t, or you can have any type of input function. So, u n plus 1 can be determined, and then you can plug in u n plus 1, y n into this function, giving you a single input single output model in discrete time domain, which means you have n plus y of n plus 1 as a function of y n, as a function of u n, and as a function of u n plus 1. So, this way we saw that one can develop an input output as well as any other kind of analogous discrete time model from the continuous domain modeling. What now we would be interested in is knowing the response of the system. For this we will require a special technique called Z transforms. So, from next lecture onwards, what we will do is we will start analyzing Z transforms of discrete time variables and see how we can use Z transforms for analyzing the response of discrete time systems. Till then, goodbye.